All right, gang. In this next presentation, we're going to talk about type 2 improper integrals. And like we did the last time, we'll just jump right in. Notice the definite integral here is from 0 to 1. The integrand itself is 1 over the square root of 1 minus x squared, okay? What is it about this that makes it an improper integral? Well, notice, gang, that the function 1 over square root of 1 minus x squared is undefined at x equals 1. In fact, you have an infinite discontinuity there, we call it. Simply put, you've got a vertical asymptote. What I've done is I've graphed the function to the right along with its vertical asymptote. Okay, so what we have over here then, this is the graph of 1 over square root of 1 minus x squared. And notice that the area underneath of it looks to be unbounded. So this looks like a similar problem to our type 1 improper integrals. The blue curve never touches or runs into the vertical asymptote. And so anybody looking at this would, intuition would suggest that the amount of area that's trapped between the blue graph and the horizontal axis would be infinite, but we know better now, don't we? Okay. It's possible that this integral may actually converge to some finite value. We tackle the problem the same way that we did before. This is how. Right? Consider that we locate some value for n, some generic n, okay? And then we figure out, well, all right, how much area is trapped in here? Then we take the value for n and push it a little bit further to the right, maybe here. And then we make the calculation again, and we get a little bit better accuracy. Take the value for n and keep pushing it to the right, gang. Keep pushing it to the right. Notice that as you do this, the value for n is getting closer and closer to 1 from the left-hand side. So to sum up, we're going to replace this integral with a new one. Where we take the value of n to approach the discontinuity, in this case, the discontinuity is 1, from the left-hand side. Okay, notice the further we push n to the right, the closer to the vertical asymptote we get from the left-hand side. So just like before with type 1 improper integrals, it's a limiting process, okay? After that, though, it's pretty much business as usual. The fundamental theorem now applies. Okay, always remember, gang, the fundamental theorem says that the function has to be continuous on a closed interval. We have a function here that is not continuous over the closed interval from 0 to 1. Okay, that's what makes this an improper integral. All right. Okay, now the first term, right? We have the inverse sine of n, where n is approaching the number 1. Think to yourself, what is the angle whose sine is 1? All right, what is the angle whose sine is 1? Well, that's pi over 2 minus. What about this one? What's the angle whose sine is 0? Well, that's equal to 0. Okay, and so therefore, again, we got a finite number. We say that the original improper integral converges to pi over 2. So in other words, go back up here. And so the amount of area you see in the figure to the right is actually a finite amount. Okay, once again, our intuition would suggest, because the blue curve never touches that dotted red line, you would think an infinite amount of area. But actually what happens is that the blue curve rises so steeply, gang, that the further you go upwards, right, the less and less daylight between the blue curve and the vertical asymptote there's going to be. Okay, and the amount of area in between those two is going to be so small as to be negligible. Okay, it doesn't add any appreciable amount to the overall area that you see in the figure. Okay, now this is an improper integral. Why? The integrand 1 over x, right, the basic reciprocal function from our pre-calculus days, gang, this function is discontinuous at x equals 0, and 0 is in between -1 and +1, right? So we have a type 2 improper integral, and the problem point here is x equals 0, the origin. Let's make a quick sketch of what's going on here. All right, so it looks like our graph then is going to look something like this. At x is equal to 1, the reciprocal function is equal to 1 also. So I'm just going to exaggerate my graph. But the closer we get to the origin, we know the reciprocal function looks like this. In a similar way. Okay, and then the area that would be trapped would be looking like this. Okay, now you can't argue symmetry, and so therefore the whole thing is going to cancel out because, gang, it looks like we're going to have two kinds of infinities here. Right, on the left-hand side, you would expect a negative infinity. On the right-hand side, a positive infinity. Here, I'll write it right here. A negative infinity plus a positive infinity. But remember, that's an indeterminate form. Okay, that means further investigation is necessary. Well, okay, here's how we do the further investigation. Take this original integral, look for a convenient value of x between -1 and 1, and usually, gang, it's the discontinuity itself. Okay, a good rule of thumb is to split up the integral when it's in between the limits, right? When it's in between the limits, split the integral up at that discontinuity. So here, that means -1 to 0 plus 0 to +1. Okay, now in order for the original integral to converge to something, these two separate integrals must converge themselves. If one does and the other doesn't, all bets are off. We say the original integral diverges. Okay, but we won't know until we actually get through it. So let's try. Okay, so here the discontinuity is at the upper limit. So I'm going to replace this integral with this new one. Okay, now we can apply the fundamental theorem. Okay, how does that look? Okay, good. Now, the logarithm of -1 absolute value, again, the absolute value of -1 is +1, so the logarithm of that is equal to 0. So the second term, really, that's out. Okay, that just goes to 0. But what about the first term? Okay, well, notice we're approaching 0 from the left-hand side of the logarithm of n, and the absolute value takes all of those negative numbers and turns them positive. And just in case you forgot, here's what the graph of the basic logarithmic function looks like. All right, the basic logarithmic function looks like this. And notice that the closer you get to 0, the further down it goes to -infinity, okay? And so therefore, this one right here, and that is not a finite number, gang. That's not a finite number. And so therefore, this integral, this one right here, we say this integral diverges. There's no point in trying to find the second integral. The first one diverged, so that means that the original integral, this one, the original integral diverges. Okay, the original integral diverges. Okay, here we have another type 2 improper integral. Notice that we're starting at 0 going to 5, but notice that the function under the integral symbol, the integrand, is undefined at the 5. Okay, in fact, you've got a vertical asymptote there. So we'll evaluate the same way that we did before. Okay, now notice the first term, excuse me, as n approaches the number 5, this expression is going to get closer and closer to 0. So the first term goes to 0. The second term simplifies to this. And again, that's a finite value. And so the original integral, we say, go back up here, right? The original integral, we say, converges to the number. What did we say? 3/2, 5 to the 2/3.